challenging on this project. So it's an area of Glasgow called Sighthill. It's been used very heavily for industrial purposes since the 1800s. After the Second World War, they redeveloped it with large high-rise tenement blocks. These have subsequently been demolished, and there's a whole new regeneration of this area of Glasgow going on. So we were involved heavily in phase one. We're ongoing now in other phases as well, but it's really the successes of the first phases. They're now actually construction has gone on there. This is what the planners wanted it to look like. Afterwards, you see this, bearing in mind this is an industrial area, has been for over 100 years. This is what they were kind of looking for. The standing stones were moved. To be honest, I'm not sure whether they were put there before or whether they're genuine stone circle. That's something I've not had a chance to research. So the introduction. So it was a design and build contract. The client was Glasgow City Council. The consulting engineer was Swaco, who have a large office in Glasgow. And there were a lot of approvals to be done on this project because of there's a lot of the different developments involved. So everything had to be approved by Glasgow City Council, by SEPA, the Scottish Environmental Protection Agency, and the National House Builders Council. So we have a fairly unique thing in the UK. So NHBC is basically funded by all housing developers. So if you buy a new house, if there are any structural problems with it or any issues whatsoever, so if you're getting radon gas or gases, contamination, settlement, etc., you are fully insured by NHBC for 10 years after the purchase of the house. So as a result of this, NHBC are heavily involved in any approvals for products being used. So this includes windows, the type of roof, and in this case, it was the geosynthetic clay liner. The consultants working for the contractor was a company called White Young Green. So I'd like to thank all of them. We all worked very closely on this project, and at times it was quite challenging meeting the requirements of the approval bodies. So this is the area within Sighthill. It's in the central area of North Glasgow. So the scheme was an £11 million, so that's about 50 million euros, over a complete 250 million program that was scheduled originally to run from 2014 to 2020. Courtesy of COVID, this is now overrun because during COVID, Scotland shut down basically all its construction activities. So this has knocked everything back. And I'm guessing it's probably costing a lot more than 250 million now, courtesy of the rampant inflation as a result of COVID and the Ukraine war. So in phase one, there were 650 houses scheduled. Some of these are social housing, so that means they will be operated by the council, and they're basically for people on low incomes and who can't afford, to say, luxury houses and stuff. There are schools, churches, park spaces. We've got community facilities and health centres. So the fundamental problem is the whole of this site is heavily contaminated with hydrocarbons and a material called Gallagher waste. And it's the Gallagher waste that gave us all the real issues. The general remediation strategy was treatment where possible, stabilize the waste products, crush if possible, bury it, and then cap it. So the Gallagher waste was the real issue. Gallagher waste is an insoluble waste product of a thing called the LeBlanc process. From a geotechnical point of view, it's thixotropic. This means a material that's thixotropic is if you then apply any dynamic loading to it or any energy, a solid becomes a liquid. So everything had to be piled on this site. So piling through a thixotropic product is a real problem. Hence the reason there was the crushing and mixing to really try and resolve the geotechnical properties of it. The LeBlanc process was a 19th century process, and it involved using sodium chloride, sulfuric acid, coal and calcium to create soda ash, sodium carbonate. And this was important for the paper, textile, glass, and soap industries. Now, the process causes very severe pollution. Byproducts include hydrochloric acid as a gas form. We've got sulfur-based insoluble wastes, but one of the real issues we had was hydrogen sulfide. So for those of you who have a background in the oil industry, you would know that hydrogen sulfide is kind of working on the oil rigs is one of the most dangerous things you have to deal with. In very low levels, it smells of rotten eggs. So it's a real nuisance problem. The real issue is when you can't smell the hydrogen sulfide. That means now the levels have gone so high and it's incredibly toxic. But also, once you get beyond the smell range, you then can, if it's mixing in an open atmosphere, you can get explosive environments. The other issue with the Gallagher waste is we also have high levels of arsenic and other heavy metals. Fortunately, the process was stopped in the late 19th century, but it's left us, certainly in the UK, with a very serious problem in a lot of the northern parts of the British Isles. So that's Glasgow, Liverpool, Manchester, and Birmingham, and also in Northern Ireland in Belfast. So the design criteria. There was 700,000 cubic meters of buried Gallagher and hydrocarbon identified within phase 1. This all had to be capped with a low permeability membrane. The membrane needed to tie into a series of bentonite slurry walls that were put around the site boundary. And the object was basically to encapsulate it all, to put it in a coffin and prevent any freshwater ingress, to stop any leachates or liquids being generated, while also being an instant and permanent gas barrier. The membrane had to be chemically compatible with the contaminants, with no long-term degradation of the membrane. So we were kind of going beyond CE marking. CE marking in our declarations of performance gives us, was 20 years. We're now moving up to 100, but kind of like the standards for NHBC is usually 120 years. They're using the same design criteria as we use for reinforced earth walls when we're working for the highways departments here in the UK. Also, the membrane had to be installed in potentially explosive environments. This gives a problem with using a classic geomembrane, because if you're doing any fusion welding, the wedge welders has an exposed plate, they're not explosive proof. So this was a problem. So that would have been the simplest and easiest concept, but we couldn't do that. Once the risk assessments were done, it was felt that the dangers of both any hydrocarbon gases and the hydrogen sulfide made this too dangerous. So we had to look at a suitable cost-effective protection of the membrane from the cover soil. So what was proposed was a polyethylene coated geosynthetic clay liner. They didn't want to use a glued membrane. On it is because, one, with the amount of chemicals that were there, no one knew how any of the problem when you glue either polyethylenes or polyprop to polyprop, the glues are they're quite complicated. The chemistry of the glues is quite complicated. So if you go to a hardware store or anything, you will see that most of the standard glues you buy, they're not suitable for plastics. So there was a concern that basically using a composite that was a membrane glued onto the GCL would cause issues. So that we proposed one that was basically, we extruded a polyethylene coating straight onto the GCL. So a GCL is made of a non-woven with a bentonite, then a woven. The non-woven is needle punched through the bentonite into the woven, encapsulating that bentonite. The object then of that process is you encapsulate the bentonite. It's now got an internal confining pressure, so that as it starts to expand, the higher the confining pressure, the lower the permeability of the bentonite. By extruding the coating directly onto the woven, we actually then bind in all of the non-woven fibers into the coating. So we're making it even harder for the bentonite to expand, so the permeabilities become much lower. So this is what the product looks like. You can see on the bottom, on the left-hand drawing there, the non-woven on the bottom. The brown is the bentonite, and then there is a polyethylene coated. And parts of the site, because of slopes and stuff, we actually made a profiled one. So we actually then have spikes on it. So not dissimilar to quite a lot of the standard geomembranes that are out there. So we'd actually looked at slope stability issues and everything with parts of the site, but I'm not going to talk about that today. They were kind of quite standard shear box testing and ensuring that as long as the interface shear angle of the material and the soils was greater than the slopes, everything was fine. We needed an instant gas barrier because the other issue is when they were planning to pile through the houses, we had to ensure we were basically going to puncture through the membrane. So it had to be self-healing and self-healing on site, and with the chemistry of the materials there, that we weren't going to see adverse effects on the bentonite. So post-installation, steel-driven hollow piling was put through, and this was then, they were put in, and we had to prove that the ceiling would actually seal round those hollow piles. And this was a requirement from NHBC, because obviously once you pile all the buildings, any apartments or houses, there will be the potential for hydrocarbons or hydrogen sulfide to actually get into the houses. Again, either causing poisonous gases, or the real problem would have been an explosive environment. So if you'd have turned your oven on, or a gas ring or a heater, you could blow up your house. So NHBC, for insurance purposes, felt this would be both dangerous and costly if so. It had to be proven that we could actually seal round the piles. Also, we had actually done another project called West Marsh. This was an area, a housing development in the northeast of England. There was an old landfill next to a new housing development. One of the ways in the UK we're addressing legacy landfills that have been before the landfill directive was imposed is we offer those developers easier planning applications. If the council own the land next to the landfill, they'll offer it cheap on the provision that they will then cap the landfill as well in accordance with basically the landfill directive. So this had happened very successfully at West Marsh. So NHBC and SEPA could go and visit the site and say, okay, this is a product that's actually been working with housing developments and was working well there. It's a multi-component GCL, so it's operating as a barrier to cation exchange. Also, if there's any high salts in the area, we get what's called ionic overcrowding. We decrease the permeability. For a standard GCL operates at about 2 × 10⁻11 meters a second. We were then going to 1 × 10⁻14 meters per second. This is the minimum permeability for a geomembrane under CE marking. Now, geomembranes actually have much lower permeabilities for this, but CE marking in its wisdom wanted us to have an actual standard permeability test. So we've set it at 1 × 10⁻14 because whilst we know we can go lower, water permeability tests can't actually measure below that because you're actually now becoming into the rates of evaporation actually within the equipment. We're using powdered bentonite. The reason powdered bentonite was a requirement on this project is powdered bentonite, you're looking at platelets then of bentonite. So the surface area to weight ratio is much better. This means that if any water or any liquids come in contact with the GCL, you get much faster hydration than if you're using a granular bentonite. Granular bentonites, then you have to allow the granules to hydrate. So if you're doing an ASTM test on a granular bentonite, you need to hydrate it for, the ASTM test tells you to hydrate for 48 hours. So the implication is your GCL may not work for 48 hours. On a landfill site or a major earthworks, that's probably not such a big deal. But bearing in mind we're dealing with houses here, we have to be gas tight. That would have been critical. No glues were allowed because of the chemistry. It's a homogeneous extruded coating. So we're not seeing any shrinkage of the geosynthetic clay liner. This was important. So if there's anything happened within the chemistry, the soil's warmed up. If it did desiccate the GCL, we don't want it shrinking around the piles. And more importantly, it's self-sealing. And it doesn't for waterproofing applications, we do tape this material, but it's not required. And for these large earthworks, we didn't need that. So this is the Gallagher waste. As you can see, there was an awful lot of different chemicals within there, apart from just the hydrocarbons and hydrogen sulfide. We've got boron, cadmium, hexavalent chromium, so stuff that's quite nasty, dissolved lead, mercury, nickel, selenium. Then when we start to go into the organics, we've got naphthalene, pyrene, benzo, atrazine, a whole host of. I had to go back to dictionaries to look up an awful lot of these, but the benzos are really quite serious because they are also carcinogenic. The shape of the molecules within benzenes, because it's kind of a flat hexagon, they're very easy to get into the skin and get into the body and can cause quite severe cancers. And although we're looking at quite low levels, remember, people are living here for maybe 20, 30 years, possibly longer. So obviously they cannot be exposed to any of these. And then we see the organics. So we've got ranging from basically hydrocarbons from C5 all the way up to C12. So really thick tars. So based on the chemical analysis, we were required to give a statement of compatibility and confirmation that our warranties wouldn't be affected. So a lot of time was spent on this. One of the ways we did look at the compatibilities that was a quick and easy test to do was actually to then take samples of these materials and do a modified free swell test. So when we use bentonite to check its quality, we do what's called a free swell test. So, and the requirement normally is you take, I think it's 2 grams of bentonite, you put it in water and then see how it expands. And the expansion is to expand it to up to 24 milliliters. So, and this means that all of the bentonite is being exposed. So what we did is basically put distilled water in these soils, left it for 24 to 48 hours, and then would filter the water out, and then do a lot of free swell tests to actually look at what was happening with the Gallagher waste and some of the other contaminants there. And we were finding that basically we were still getting free swell of the bentonite. So that gave us a reasonable degree of confidence. But then we also, there was, our technical departments and our product managers in head office were kind of kept quite busy looking at this. One of the other things we had to do is we also needed to confirm the chemical compatibility of the cover soil, because the cover soil is, when we installed the composite GCL, the membrane is on the base covering the Gallagher waste. So bentonite is exposed at the top because then it's, remember, it's a membrane, woven, bentonite, non-woven, and then the cover soil. So we also had to check this. One of the issues with the cover soil was because a lot of it was coming from within the city. Some of it had when we checked the particle sieve distribution charts, we found that we were getting quite high, well, shall we say, an unsatisfactory level of coarse material, far beyond, because usually we just like a sand type material going on top of a GCL. So once we looked at this, we proposed using a 500 gram non-woven geotextile. Basically, then field trials had to be done with the 500 gram with the cover soils proposed. So they would compact the material, put any cover soils on top of it, and then it would all have to be dug out by hand so that we could actually then inspect the GCL to make sure that we weren't getting puncturing of the GCL, or what the main concern was, we were starting to get deformations of the GCL, so the bentonite was maybe starting to be pushed out and extruded. So again, a lot of tests were done on this. So we found that we used a particular grade of a 500 gram. So we were looking for a high CBR material. We wanted the extension to be kept as low as possible so that we were mobilizing the tensile forces of the GCL as as fast as we could to ensure that we were getting a bridging within the geotextile, so we could ensure we were reducing the point loading on the GCL. So really, they're all the technical issues. I said we can go on with chemistry forever, but that gets far too complicated. This is actually Site Hill. This was a fairly unusual day for Glasgow. It's sunny. For those of you who've been to Scotland, you'll find that there's a reason why there's so many locks up there. It rains a lot. So this is the material then being capped. So that is the Gallagher waste that's been mixed in with sands and crushed aggregate, really to deal with these thixotropic properties, to actually make it, from a geotechnical point of view, acceptable. The GCL has gone on, then there's a geotextile on top, and then the cover soils. You can see here, so here's the GCL going in. One of these, the way we ensure that it's all self-sealing is there is a 300 mil overlap. In the top non-woven of the geotextile, we impregnated this with accessory bentonite. So all the longitudinal overlaps, basically, they just have to ensure that there was a 300 mil overlap, and we were done. There's actually, you can see it looks like this. We actually were impregnating the bentonite with 500 mil of bentonite, just to ensure that there was a factor of safety in case there was any issues. And we also have to be clear that we don't want stones in the overlaps. So there was a very, although this was a contaminated land project, we were using the same level of construction quality assurance, which is what White, Young and Green's main role on the project was, to ensure we're not getting any stones within the overlaps. They were kept clean, otherwise they wouldn't be gas tight, and that would cause problems. Panel layout drawings were dealt with both by ourselves and White, Young, Green to ensure then that basically that the thing was all capped completely, and then we would add accessory bentonite to the end of the rolls, and at the end of the rolls it would be a half-meter overlap. The GCL was keyed into the slurry lagoon. This is one of the reasons why they were quite keen to use a bentonite-based product as well, is because they felt this would be more compatible with the cutoff, the bentonite slurry cutoff walls that were going in. So it was easy to cut in. And with the high friction angles that a GCL has over a membrane, there was less concerns about this pulling out once it was compacted in and covered. You can see that parts of the site were right adjacent to what are basically already a lot of houses. So these are from the 70s. These ones built here. Then on areas that are not actually covered by Gallagher waste. And when this was the developments there, you can see in the background, basically in those days, they would just dig it all out and ship all the waste off to a landfill. We've kind of tried to move on from those days because what we don't know with the adjacent developments is how much damage did they do to the water table, the exposures to people from the Gallagher waste, how much was then become airborne because of the heavy metals and stuff. So, and of course, there's also the great unknown here, which was not an issue for us as regards chemical compatibility, but there's undoubtedly asbestos in this site as well. Again, more of the GCL and the 500 gram geotextile going in. As you can see, when it was a dry day, basically the waste just looked a lot easier to deal with. There were no issues with it. The big issue came, and this is where everybody started to get worried. NHBC decided although they'd approved the material to be used, they then decided after installation, we want to do some real on-site trials on the as supplied, basically cover materials, the as installed GCL. So this was a bit of a surprise to everybody at the time because we thought we've done the field trials beforehand. So NHBC said, no, we just want one final check. So a piling rig was brought on site and they piled through the cap, through the cover soils, and then we excavated down As you can see, although quite a lot was done by machinery, once we got close to the GCL, everything had to be done by hand around the pile. So we could actually see what the GCL looked like having been punctured through. And what they wanted to do was to actually see at close contact of the pile and would monitor it for several days, was there actually any gas escaping? This gave us a few causes for concern, because when you install a GCL, the recommendations, both by the regulator and ourselves, is to cover the material within 24 hours with a minimum of 300 ml material, and then you put your cover soil on. So in a landfill, reasonably quickly afterwards, that's a MESA, so that we get an increased confining pressure on the GCL, so we keep the permeability as low as possible. So NHBC wanted to leave this out and check it. So this was kind of if you like, almost a test to destruction of a material. We're going beyond our recommended guidelines here. So they were checking for gas. So gas detectors were put in. They were using flame ionization detectors. Hydrogen sulfide monitors were put in. Basically the same ones that are used on the oil rigs. I can speak with experience because I started my career as a mudlogger. I didn't work North Sea, but I did work with Shell Oil in the Middle East. And hydrogen sulfide was a big issue for us. So hydrogen sulfide was checked for. We found virtually nothing. So NHBC then ratified the product, approved it, which was kind of quite a big feather in our cap, because as you can imagine, we've now installed over, at this point in time, something like over 100,000 square meters of product have been installed and buried when NHBC pulled this Joker card on us. But it all worked. So that gave them the confidence they wanted. Everybody was relieved and happy. As a result, this is what phase one looks like today. So there are now parks there. The first of the developments have gone in. And we're now looking at moving up. So we're now working currently on 2 of the other phases. And that's me finished, really. So an unusual event for me. And not only am I on time, because I started early, but I've actually kind of gone through the right length of time. So yes, thank you all. And yeah, I hope you found that useful. If anybody does have any questions or wants more information on the project, then please don't hesitate to reach out to the NGO, and we'll deal with any queries. Okay, thank you.
Thank you very much, Christopher. I don't see any questions in the chat, so if anybody has a question, you can also raise your hand and just ask it, or you can type it in the chat, whichever you prefer. I see a question showing up now. Why they didn't think of piles under the membrane? Not sure. I understand that question.
So the reason, so the piles, the issue with the Gallagher waste is because although they mixed aggregates and things with it, it's thixotropic. So there were still concerns about its overall geotechnical properties. So it was a requirement by NHBC that any structures had to be piled through the waste to natural ground, basically to bedrock. So the net result was we had no option but to pile through the cap. And that was the great conundrum at the very beginning of the job, because realistically, that's the last thing you ever want to do. But it's something we've been involved with now for several years. We did a big job. The first job we ever tried this with was, but it was just with the standard geosynthetic clay liner, was in Belfast. Because the problem you've got with some of these cities is, especially in the 1900s, you have a small city and they will put a big landfill right next to the city, and then they've expanded over it. And as time's got on, we've realized that's a really bad idea to be building up. The geotechnical properties of an old landfill is a disaster, to quote my old boss. So you have no option but to pile through them, but that means you're piling through the caps, and it's how to deal with that. It is a challenge.
Here, thank you. There's a question from Adam saying, I probably missed the part, but what was the influence of the chemicals on the permeability of the bentonite? Do you have any quantitative results?
Yeah, no. So we also, I should say, free swell was the most aggressive test we did, looking at the quality. but we also use that filtered water in some permeameter tests to actually do long-term perm tests, and it didn't affect the permeability at all. We didn't do it on the multi-component one. We did it just on the standard GCL, because obviously otherwise we're just testing the permeability of the membrane. So we did some, I should have said that, I apologize, but we did some standard ones. That was difficult to do because getting a permeameter to put contaminated water through, head office didn't want to do it, so we had to buy a permeameter and get those tests done here in the UK. And that permeameter, after all the tests, had to be, all the casing and everything basically was disposed of. So that was a requirement by SEPA.
That's clear. Can you maybe elaborate a little bit on how because you mentioned on previous projects you've seen sealing properties of the combined membrane liner, really, and how much sealage you would get even after piling. How was that tested? Was it a visual inspection or?
No. So well, there was the visual inspection at first, one to see if there was any damage, if the pilot created any extra damage, or it had just sliced straight through. So it had sliced straight through the GCL. But what they did for 48 hours afterwards, while it was exposed, they set up gas monitoring. So they did original gas monitoring to see if anything came out originally. They had checking. So that's what they were using, what's called an FID, a flame ionization detector, see for hydrocarbons and for hydrogen sulfide. But then they would leave monitoring stuff there actually strapped right down at the base, because things like hydrogen. Because now we've got an excavation, so they didn't want people going in there every day basically. So we put monitors in. So for the hydrogen sulfide, we were using basically the same monitors that are used in the oil industry on an oil rig. So the hydrogen. So while you're drilling on an oil rig, that you'll actually strap hydrogen sulfide detectors to the blowout preventers, because that's in the cellar, because that's usually where, because hydrogen sulfide is heavier than air, so it'll collect in there. So, and the hydrocarbons is the same. So it was kind of like, especially for those gases, methane, not so much, that's lighter, that'll come out. But anything like carbon monoxide, hydrogen sulfide and stuff, then we were seeing that would putting monitors in the base and leaving it for a couple of days would be quite a robust way of actually monitoring.
Yeah, that's clear. And was any gas collected as part of the project? Because you might consider, there's a maybe a buildup of gas over time. Was anything installed to?
No, there was. There was none. So realistically, this had been. Remember, most of this waste has been from. It was placed there in the 19th century. There's been an awful lot of building and demolition works gone on this site beforehand, and it's the Gallagher waste is very low permeable. It looks like clay. It's kind of like a blue color. It's high permeable. It's a very low permeability material. So the gases you're getting are in low concentration. So the real issue was it then concentrating within houses and stuff. So there's no concern about open areas. And again, they didn't want to put in passive vents, so that, because again, it wouldn't have been an effective way of extracting any gases, because you're talking about the permeability of the Gallagher waste, probably untampered with, is kind of like about 1 × 10⁻⁷ meters per second. So you'd never be able to extract anything of any meaning.
Right, that's clear. Right, Christopher, thank you very much for the answering the questions and a nice presentation.
Okay.
I'd like to ask Adam to share and start his presentation on possible failure modes for reinforced walls. Yeah. I don't think we can hear you, Adam. I can't see your screen either. Sorry, I have no sound. I don't think anybody's hearing anything. Which is strange because we tested it before we started. That's usually what happens with this technology. So please, everybody, hold on a couple of minutes whilst we try to fix the issue.
Something now on.
Yeah, I can hear you now. Yeah.
You can hear me now? Okay.
Yes, great.
And, that works. And you can see the presentation now?
I think it's coming up now. It's loading. Yeah, I can see it now. Yes, thank you.
Yeah, after this bit slow start, now we can go on with the second presentation. I also want to thank the NGO to invite me for this presentation. When I look at the program, it looks like this presentation is a kind of prologue for the presentation that is coming by Mark Knotts. But I have to say, completely independently. So I hope there's some same ideas, but you will see that at the end of this workshop. So I will look more to possible failure mechanisms. So I will show some project, but not too much. Most of it is research, physical modeling research that is done at Altaris and Kent University. So it's not an international project, but it's international research. And I used a lot of research from others to name Wittekoek, Jonathan Aiken, and my PhD student Hamzat Ahmadi. So Wittekoek and Jonathan Aiken were working at Altaris. I will give some introduction, some examples, requirements, and then discuss on possible failure modes, depending on the kind of structure, and to end with conclusion, and especially then what is the use of these physical modeling compared to numerical calculation. Yeah, I think most of you know what is a mechanically stabilized Earth wall. It's you can see here the idea. So you have a soil body, you have reinforcement, and the reinforcement keeps the wall in place. So normally, not always, but normally the reinforcement is connected to the wall to prevent turning over of the wall. Now there's already quite some experience with these walls, and they go to very high walls, as you can see here. So this is a really high reinforced wall, and also this one, it's really quite an impressive piece of work to get a wall in this difficult surrounding. But as you can see, it can be done. There was even in the invitation of this event, there was you could see some reinforced wall. As you can see, I don't know if you can see my pointer, but you see in the roads here, you see several reinforced walls that were used to make these roads. And what is more, it's not only that you have a high wall, but you have a high wall with loading on top of it. It makes, of course, things a bit more complicated, and that is also what is of importance in the remaining of my talk. So that you have not only a wall, but that you have a wall with the loading on top. Now the idea for a simple wall you see here on the left-hand side, and so what I showed before, you have the geogrid connect to the facing, and now you can make because the geogrid keeps counteracts the active earth pressure over here. You can make these vertical facing. If there is loading on top, like in this, where you have a kind of a bridge, then you need, of course, sometimes some extra reinforcement below that to keep everything stable. As I said, it's not very new, and you saw already the examples. There are in the Netherlands there are design rules. So here you see the design guideline for these reinforced walls, and it's already the second edition. So there is some knowledge and there is some experience on that, and therefore you could raise the question: is it necessary to make another experimental research program, because we know already quite a lot on this? We know, for example, that there are that you have to design such a wall according to the book I just showed you. You have some 8 calculation steps after the initial details of the soil, of course, so parameters. There is some global dimensioning of the structure. Then you have to look for settlement, especially in the Netherlands, where you have very soft soil. You have to realize that if you build something like such a wall, then it could settle into the soil. Of course, the external stability, so that the whole structure is going to move. The details of the reinforcement and the internal stability. And then at the last is more the architectural, the facing, what kind of facing do you want? And still construction-wise, what kind of connection do I make with the facing and geogrid? And what kind of deformation do I allow? Because geogrid have always a certain flexibility, so there will be some, there can be some deformation that has to be taken into account. In this presentation, I will especially look at the internal stability, because that was where, for the structure, I will show in a moment some issues arose, what can happen there. So that is in the research we looked especially to that internal stability. Now, once more, some examples of the external stability, just to have an idea. So it can be not stable at all. So the bearing capacity of the soil underneath, horizontal slip, and a deep slip surface. But I think you all know that. For the internal stability, there are also several modes. It could be that the tensile force here in the geogrid is too high and that the geogrid is torn apart. But it can also be if this triangle tries to slip down, that it takes out the georectal, that it is pulled from the soil, and that therefore failure occurred. And another one is that one part just slips over the other part. Now, as I said, it's already well known. So why research and the research at Altaris especially started with this project. And that was a bit different from the normal reinforced walls, because it's reinforced sheet metal wall. As you see on the right upper picture that it is a sheet pile that is connected with G connection you see in the picture at the bottom. And all together make something like you see in the cross section on the left hand side, and it's all for a windmill park in the Krammer, which is in the southwestern part of the Netherlands, in just between Zeeland and the province of South Holland. And why these sheet piles need such reinforcement? That is because of these windmills. They are, as you know, they are quite huge structures, and these structures have to be placed there. And to do that, you need a crane, and that crane, that can be close to this sheet pile wall, and that crane is very heavy, especially when it has to lift these parts of the windmills, and such a crane can brings a lot of load into the soil and can therefore give instability of the structure, and that should be prevented by this geogrid anchorage. Some other examples, not much examples, but I found some in a Geokunst article from Dieter from Husker, and he showed a temporary bridge, and this is not really a sheet by wall, but it's the Berliner wall they make in Germany, which is reinforced by geogrid. It looks not such a very impressive structure, but you have to realize that it has to hold 40,000 passengers of 74-ton truck, so it's really loaded quite heavily, and it should remain there, of course. And a permanent structure you see here, so that it's also not completely sheet pile wall, but it looks like so. You have hollow piles over there, and in between encapsulated geotextile columns that all together should make quite a stiff sheet pile wall. And on one side you have soft material, so this in Dutch with this peat and organic clay. And on the other side there is the autobahn, which is 50 meters high on an embankment, and it should be this all should be stable, of course. And to do that, there is the geogrid that keeps these construction of piles and encapsulated columns in place. You see the picture how it looks like, and you can also see on the right hand side that it works quite well. So after half a year there is 5 centimeter displacement, and when you look at the these are piles of 21 meters and this is 50 meters of embankment, then such a deformation is of course quite limited. In the same article, they gave some ideas on how it works. So such a sheet pile wall with reinforcement. There is an active zone that will not contribute, and there are geogrids, and in the passive zone, the geogrid has a friction with the sand, and from that there is a tensile force here that keeps the wall in place. And of course, as a consequence, if you make the geogrid too short, then they will not work. So that was the idea in 2019, but people were not completely sure, and therefore the research started. So, and what is the difference from this kind of structure compared to normal reinforced walls? Is you have here you have already a slope, and so it's difficult to make the geotextiles very long. So you don't want to make them too long, because then you have to dig out all this which is already there and to replace it, and you don't want to do that. So you want to have this a bit shorter. That's also possible because you have a high loading on top, and the loading will decrease when you go down. So, and another difference, of course, that you have, that's an advantage for the sheet pile wall. You have a very stiff foundation, so it cannot move easily, and of course that will give some extra stability. But when this was developed, there were some questions raised, and one was the result of numerical calculations that from Dine did. I forgot one N here. It should be one Dine. And he showed that the friction. So the idea is, when I go back, here you see that on both sides there is friction, but he realized, based on the numerical calculation, that that is not the case, because if you have if the soil starts to move here, then all soil on top will also start to move. So that will not really work, and what only the friction here below will be will contribute. You have to realize that if at some place the friction is the force is higher than the friction, then it could be that the whole structure is going to move. That was not completely new, because I will not go in detail, but it's more or less the same reasoning that was followed years ago by Professor Verruit at Delft University, who said, "Oh, when you calculate the stability of such a wall, you should not assume that it is that there is friction on top. There's only friction at the bottom, and because the weight is higher and higher, so you can have more and more friction at the bottom. But if it is overcome at one place, then the top layers with the geogrid, they all will move." Now, so there was a reason to do some testing, and here you see the setup of the small-scale tests that were done at Ghent University. So we had a container of sand, 80 centimeters high, different layer of geogrid, maximum 8 layers, but also with 4 layers. We had a loading frame to give extra load. We could measure the deformation, and of course it all logged in the computer. The experiments that were done at Altares were even on a smaller scale. So as you can see here in millimeters, so it's half a meter and 30 centimeters high. It's quite comparable. It's also geogrids here in the sand, and you see here facing wall, and the loading is not by the hydraulic plunger, but the loading is simply by filling this container with water, and the more water you have, of course, the higher is the loading, and that could be done until it fails. You could think about why small scale model test, because for the situation without loading, there are already large scale model tests, and it appears that there is for large scale or for without loading. So if you have just a reinforced wall, then at large scale is necessary, because in a large scale you have that the pressure is increased, and if you have small scale, then you have lower pressures and it does not fit. But here the situation is different, because here you have the loading, and that loading is far larger contribute that than the weight of the soil. Right? So that therefore you could do that, and that is proven by this experiment. So it was at what is called the creative sessie that the Dutch chapter also sometimes organized. So here people have to not only to think about reinforced walls, but they have to build one and they have to test one. And here you see there's a very small reinforced wall. And you see if you do it well, hey, so these I think these had won by that time. They made a very good wall, and then you can have an enormous vertical load on it, and you can see this vertical load of these 3 people on that wall is much larger, of course, than the weight of the sand here. Right? So you can use, if you have such a large load, you can use a small scale model test, and you can make the stresses from this load the same as the stresses you would expect in the prototype, and then you can use the results. Now here you see such an example. So this is in Ghent, and that was more general. So it's still you can say a traditional wall. In this case, a wall without any facing, so only soft facing is here. And then by using image processing, you can bring a load on top, and then so the load is if you bring in that load, then you see by image processing, if you look at the shear strain. So here the colored plot is shear strain. And blue is very little shear strain, and red is, of course, a lot of shear strain. And then you see very nicely that there is a straight failure surface that goes from the loading to the wall. And at the top of it, there is a bit more. At the top, you see that there is also some movement of the geotextiles that brings extra shear strain as a result. Now here you see it once again. So you see, but now with the load, you see that just exactly behind the load, the failure surface starts. And you also see that the different layers of geotextiles. So that was a test with 8 layers of geotextiles, and it was relatively flexible geotextiles. It was even non-woven, but you normally would not use for reinforced wall. But it was just to show what kind of deformation you can expect in such a wall. And you can look at the shear strain, but you can also look at simply the vertical displacement with such image processing. But it's a bit difficult to show that, because you have here you need a 3D picture to show that on every place. So what I did is here you see the reinforced wall, and if I put that down, so that you and then look at what is the vertical displacement, then you see the higher this level is here, the more vertical displacement is available. So you see that each geotextile that you see here, hampers, of course, the vertical displacement. And that is, you also see clearly that there is a failure surface, because at the left of the failure surface, which is in fact over here, there's of course more vertical displacement than there is in this area with this situation. But also here you see some vertical displacement. If you just think it's a bit complicated to look at it like that, so you can also take, of course, the vertical displacement of just one line, and then you see something like this. So you see that there is a geogrid goes downward. There is a vertical displacement. It is along a geotextile, and here you see the slope is steeper than in the other areas because that is where the failure surface is. So, and it looks here, of course, if it is very steep, but that's not the case, and because the axis is, you see here it's only to 140, and here it is to 2500. So the vertical axis is very different from the horizontal axis. So in one of these arbitrary units is 0.2 millimeters. So if you have 20, then you have 4 millimeters or so of displacement. That's a bit the ID. So they are quite limited, the displacements. And the same way you can look at the horizontal displacement, and that is interesting, because what you see then is that again you see, of course, there where the failure surface is in a triangle, you get also more horizontal displacement going to the left, so the wall is bulging out more or less. But you see that the geotextile is also moving in this part outside the active zone, which is this out. The geotextile is moving more than the sand. So that means the geotextile is pulled out of the sand, and that's even very much the case here, where there is only limited vertical loading on the geotextile. But what is of interest is to see that. So here you see that the geotextile is pulled out, but here it's working in the other direction. So that means that also here the geotextile is pulled, but not to the wall, but from the wall. So you get the highest tensile force, and here in this location at the failure surface, and that's also what you saw, what is normally expected is. So you have the highest force is here, and also here the horizontal loading on the wall itself. So over here it's lower than what you expect just from soil mechanics, because the geotextile compensates already some of the horizontal force. Here you see the situation close to the wall, and then you see again that there is geotextile, the movement is less than where there is no geotextile. And overall there is the bulging of the wall because of the loading. So that is the situation with the soft facing, and these active stress here is less than the active stress in the soil, because the geotextile helps you to bring to have a lower stress over here, and that also means that for the design you don't need too much worry about these active stress here at the facing. So and the tensile force in the geotextile looks a bit as drawn, the red line. You see here the highest is in the failure surface, and that's also where you possibly you can get cracks of breakage of the geogrid. But that was more in general. There are still some questions remaining, especially for this structure. How does a geogrid anchor provide resistance in a specific situation of strip footing surface loading? We saw something, but here we have different geotextile geometry. And what is the influence of the position of the church load, the length of the geogrid, a second geogrid, and connection of the geogrid and the wall? So for the research for this, there was only limited amount of geogrid, so of one, either one or two. Here you see once again the setup. What I showed already, if you look very carefully, you can see the geogrid over here and the second geogrid over there. It was one which was really a drawback of the small scale method is that you could not make a real sheet pile. So here it is a silicon block. It should represent the sheet pile, which in reality goes much deeper into the soil. But that was, of course, not a very good situation. This will behave differently. So in some tests, they saw that the lower end of the sheet pile was moving, and you would not expect that in the real situation. The geogrid was connected to the model sheet pile, and it all was done by test scale 1 to 60. An interesting result of this is that different from what I showed you in the beginning, what is still the common idea, is that such a geogrid also has an influence when it is only in the active zone. So I showed you in the beginning that if it was within the active zone, it would not work, but it does work to some extent. So if you have 11 centimeters of geogrid, then you can see, if you look at the applied load and the displacement, that is much better than when you have no geogrid, which you have here. The applied load is only minimum, and then you get already a lot of displacement, so you get failure. And to reach the 11 to reach this level, it was essential that this geotextile was connected with the wall. If it is not connected to the wall, it will not work. So then you get this black dotted line, and as you can see that it's hardly different from the situation without any geogrid. But if you connect it to even 6 centimeters, so somewhere halfway, then already there is some reinforcement by the geogrid, and of course the real reinforcement comes when you have also geogrid in the passive zone, as you can see with the 18 centimeter. Then it's much stronger, and also the deformation remain quite low until, in this case, 4 kilonewton the meter, and then you get the higher deformation. So that really makes, of course, if you have the possibility to make a long geogrid, then that's certainly a lot better, because then all the other ones are failed already. So at that force. But the difference in idea, so this was something that needs some rethinking, because the idea was always, if you are in the passive zone, if in the active zone, there is no influence at all, and there is there is certainly an influence. And I have to go back. How does that work? And if you push this down, and if the geogrid is connected to the wall, then the geogrid also goes down a bit here, and yeah, it pushes a bit on this sheet pile wall downward, and therefore some of the loading is going to the sheet pile wall, and it's not directly pushing on the failure triangle anymore, and therefore you get a more stable solution. If you look more in detail, now in a small scale model test, that is a bit difficult, but yeah, if you compare these small scale model tests with the numerical calculation, then you can see a bit more. And what we discussed, that the tensile force is was the highest here at the active failure surface, and that decreases when you go to the wall. That is the case when you have a normal situation with a flexible wall. But if you have a stiff wall like a sheet pile wall, then yeah, when you push it down here, then it will here still pull on the geogrid, and resulting in an increase in tensile stress on the geogrid. And you can see here, so this gives the result of a numerical calculation that are shown below at the loading of 5 kilonewton the meter on this geogrid. Then you see that in this area the geogrid is pulled out of the soil to some extent. So you get some due to that, the tensile strength is of course of tensile force in kilonewton meter is of course 0 at the end of the geotextile, because there's no way that it can have a force that has to be built up by friction, and you see due to friction that increases. Now then you get the first the critical slip surface where you get some movement over here, and the tensile force increases, goes down a bit. But here in this area, so different from a situation with a flexible wall, it increases again, and the increase is only limited, but there is still quite some tensile force which stabilizes this sheet pile wall. The advantage then of the of a numerical calculation, that you can see what comes from top and what comes from bottom, and then you can see that the so if this is negative, then it's stabilized, and that's from you can see from the bottom that is much more than from the top, which is only there is some here at this area. The top also gives some contribution, but here it is more or less around the 0, and this one gives. So that is how the friction force develops. So that determines how much the geotextile moves compared to the soil. And you see that here this is more negative. It means that there is more friction here at the bottom than there is over here, and that is because of the loading. You can have you have a higher vertical stress, and due to the higher vertical stress, you have also more friction. Now, for the second geotextile, you can see that even here. So if you look only at the total, that the total tensile force increases, and that means that it also contributes to although it is up to the failure surface, it really contributes to stabilizing this wall. So if you look once again to the remaining research questions from how does a geogrid anchor provide resistance in the specific situation of strip faulting circuit load? Now, by the geoductile is fixed to the sheet pile wall, that limits the vertical movement, and that's also a contribution, and that's a contribution that works already for short geoductiles. Now, in the friction of the GR in a passive zone, but also in the active zone, contributes to the stability again when it is connected to the sheet pile wall. And what is the position of what is the influence of the position of the short load? I didn't go to that in detail, but that determines the shape of the failure surface. Of course, what you expect, the length of the geogrid, it works already for short geogrids, but the longer, of course, the better. That is not very spectacular, such a result. And the second geogrid, you need some deformation before that is becomes effective. So if you want very limited deformation, then you can wonder if such a second geotextile is necessary. And the connection to if you have a stiff wall, then also the connection is quite important to stabilize the wall. And then I come to the conclusion, and especially from what is the physical modeling research now? What is useful? Is it useful because the problem of the sheet pile wall in Kremer was, if we say, if we are honest, it was solved by field tests that was done and numerical calculation. Why would you need such a small scale testing? And I think the advantage is that you see the influence of different parameters, the length of the GR, the connection, the position of the load, and the stiffness, and that can be tested very quickly. And by the image processing, you see in detail the failure process. I hope I showed you something. And if that corresponds, and that did correspond in our case with numerical calculation, that gives also confidence in the numerical calculation that you can use these calculations. It shows what happens and how what kind of failure you can expect. And of course, that helps you to prevent that. And that was my presentation. I thank you for your attention.
Thank you very much, Adam, for your presentation. That was very interesting. To me, especially surprising to see the influence of the geogrid in the active zone and how it still contributes. That's not something I honestly would have expected before seeing this. I don't know if there are any questions from the audience. If there are, please feel free either to raise your hand and ask them or to send them on the chat. And if not, I think it's a good idea to continue with the presentation by Max Notz, because we have a little bit of time, I think, to make up. Oh, there's a question from Jason. He's asking, was there a scaling effect to the physical model you developed? And if so, how did you accommodate for the difference in results compared to the full-scale case?
So there is some scaling effect because we pull out floors outside of the loaded zone, and it's higher in reality compared to your small scale model test, because the amount of geogrid, the amount of soil on top of the geogrid is less in small scale model. In within the loaded zone, so there is as I mentioned, there is no real scaling effect because you can there you can have the same stresses in reality as in the model. Right? So of course you have to use the normal scaling laws as a use for also in centrifuge testing. So your sheet per wall has the stiffness has to be changed, and but if you do that correctly, because the stresses are the same as the model and prototype, you can expect quite comparable results.
Okay, I think that's a clear answer. Thank you very much, Adam, for your interesting presentation. Please, I would like to ask Max Notz to share his presentation on the large-scale reinforcing geosynthetic project examples in Africa.
Good afternoon, everyone. Can everyone hear me?
Yes, I think so. We can see your screen as well. Oh, I think it's just
starting
starting up.
Visible. Excellent. So then I will start with my presentation. I will be discussing or presenting two different project cases. One of them is an mechanically stable.
Sorry, you're sharing, I think, your screen over 3 different screens now, as I see. So it's not one full screen, but it's 3 different screens. I don't know if you can change it. If not, I think it's okay to carry on. But basically, you're showing
3 different screens.
Yeah, a couple of miniature versions on the top right. You're showing, but it's not full screen.
How does it look like now?
See anything yet?
Everybody.
Can you see one full screen?
No, I don't see anything yet. So I don't know if you are sharing.
Just a second. I will start sharing again. Boop, boop, boop.
Yes, that looks better.
And now I start the presentation mode.
See if that works. Yeah, I still see it shared on 3 screens. But I think that's okay. The biggest screen you can see.
What does it look like now?
Yeah, it's still the same. So I think we can see the next 2 slides miniature on the top right.
The other option could be, of course, that you start a presentation from your computer, but I'm working on a Mac, and there's always an issue somehow between Mac and Microsoft.
Oh yes. I think this is fine, Max.
This is fine. Okay.
Yeah, it gives us a preview of the next slide, so then we can mentally prepare for what's coming. So that's also good.
Okay. Very good.
Well, thank you.
First of all, thank you very much, NGO, for allowing me to share some of our experience in Africa. I will present 2 different projects. One of them is a project in Ghana, which is the Pokuase interchange. And the second project is a road project in Uganda. But I will start with the first one, which is basically an example of different MSE structures, mechanically stabilized earth structures, of the types that Adam was presenting before, although his focus was more on scientific research and lab testing. And my focus will be more on presenting how it works in practice and what challenges the project actually brought us. The second presentation, the Oil Roads Hoima project, was basically prepared by my colleague in Uganda, which is Brian Okello, and I would like to thank him very much for supporting me in that. Start with Pokuase interchange in Accra. As you can see here, the project team, the client was Urban Roads, which is part of the Ministry of Roads and Highways. The contractor was a Chinese one, Zhongmei Engineering Group, and the design and supervision consultant was Associated Consultants, which is one of the largest local consultancies in civil engineering in Ghana. And the engineering and the supply of materials was done by Admir Africa and Gesynthetics. Now, interesting to know is that part of the funding of this project was by the African Development Bank and part was done by the Ghana government itself. Now, the project itself falls under urban roads, like I mentioned, which is part of the Ministry of Roads and Highways. And the first design concerned a three-tier single-point urban interchange, meaning 3 levels of roads going over each other. Due to a proposal for value engineering by the contractor, they changed the designs into 4 levels. And 4 levels. I will show you pictures at a later stage, but this implied that there was even less space for bridge approach roads, and they were forced to work with vertical retaining structures in order to make it possible. In the end, we used in the interchange itself 24 MSE structures. I will show you later. With concrete facing panels, which were prefabricated. And in other roads approaching the interchange, different concrete block faced MSE structures were constructed as well. The stability analysis was in line with European Code of Practice number 7, Code of Practice for Geotechnical Engineering, and also followed the British standard for reinforced road structures. At the time of construction, which is about 3 years ago, 2 to 3 years ago, it was the largest interchange of the West African continent. And when you will see the pictures, you may understand. Now, where does it lie exactly? Here on the right-hand side, you can see the country of Ghana, and the capital of Ghana, Accra, is at the coastal zone here. More or less halfway the country. Just to get an idea of the location, here we have Nigeria, here we have the Ivory Coast, and Ghana is a very large country, which just to give you a scale effect, it's larger than Germany, just although it may seem very small if you look at an African plan. And if you zoom on Google Maps, you will find the interchange here on the northwestern part of the Accra metropolitan. Now, we have been talking about MSE structures before. The basic principle is a reinforcing element is connecting the active and the resisting zone, and as such creating a stable situation. Now, the actual execution of these type of works can provide different appearances, which you are seeing here on the right-hand side. You can either use sort of a block wall type of panel solution. You can also use gabion types of solution. You can use concrete panels, full height or segmental, but you can also create green slopes up to certain angles as long as the green vegetation has a good condition for growth. And here we can see a top view of the project still in the construction stage. Here in the background, you can see that indeed there are 4 levels of interchange. Here you have the base level, then you have the first flyovers here. You have some flyovers going on the 3rd level, and the top level here is giving you the final flyover structure. And you can imagine that there's very little space for creating vertical structures, and therefore vertical retaining structures were in the project from the start. The only innovative thing was that it was in the end it was constructed as a mechanically stabilized earth structure instead of traditional concrete retaining structures. Now here on this point you can see one of the walls, and just to give you an idea of where that one is positioned, you can see on this top plan or view, you can see the wall which is indicated here, which is mechanically stabilized earth structure number 16. At the same time, it also gives you an idea of where all the other retaining structures in the same project were positioned. So for instance, this long wall, which is MSE number 15 is going on the opposite side, starting here somewhere and going all the way to the opposite side, to the, let's say, the southeastern side of this in this picture. The original proposal that we made was working with full height concrete panels. What we learned from the presentation by Adam Bezuijen is that it is very important to have a good connection to some sort of a facing panel or a solution like a wraparound structure. Otherwise, there may be too many displacements at the facing. In this case, we worked with what we call a passive system, meaning that you first build the MSE structure like a wraparound structure, and at a later stage, you can put a prefabricated panel and make a connection to the existing wall. Now, this was the first proposal that we made with a full height concrete panel, because we had a lot of experience with these type of structures in Nigeria and also in other countries. But in the end, the Chinese contractor, they decided to develop their own panel system, which I will show you later. But it shows, yes, was someone asking a question? No. Okay. But it shows that this was quite an impressive, very large scale project. This is the end result, and what already shows, what already strikes is that these are different from full height panels. In fact, what the contractor used were very small segmental panels, and they constructed vertical concrete beams and horizontal beams with slots, which allowed these concrete elements to be slided from the top into the panel structure. The other location, which is not directly at the location of the interchange, block wall retaining structures were used to landscape the area, the environment. As you can see, those were not that highly loaded from the top, because there were no heavily trafficked roads on top of the wall. And the landscaping architecture became very creative in creating these type of staircase structures integrated into the wall. Now, in the design process of the MSC structures, the starting point is the Eurocode 7, which is sort of the starting point for all kinds of geotechnical engineering and structures. Embedded in the EC7, every country has this possibility of making its own set of rules, and this in fact also happened in Germany and in Germany and in the UK, but also in Holland, like Adam was presenting. But we worked with both the German standard, where the recommendations for the design of earth structures, reinforced soil structures, is embedded in the so-called NGO, and in the British standard, it is embedded in the BS 8006, which is the code of practice for reinforced soil structures. Now, both these codes are evaluating and analyzing the ultimate limit state, serviceability limit states, and the ultimate limit states. So two different limit states need to be evaluated. One of them looking at the possible failure by shear break or the breaking of the reinforcement. The other serviceability limit state needs to evaluate the possible settlements of the structure or deformations. Now, these codes are both presented here. On the left-hand side, you can see the German code, the NGO, which fortunately is also available in the English language. And in the middle, you can see the British standard 8006. Now, those two codes can be used for design practices. On the right-hand side, you can see a code, a European, the EN 14475, which is the code for the execution and construction of reinforced structures. So that one is more important for the actual construction of the works. What we did is we implemented state-of-the-art software to do the stability analysis, and here you can see the layout of one of the bridge approach structures. Different geogrid layers are embedded in the vertical structure, and after doing that and bringing in all the specific material-specific properties, an analysis was done for different loading cases using Bishop methods and vertical slice methods. And three different loading cases were evaluated. One is the permanent situation with live loads and dead loads. The other loading case was permanent situation with live loads and dead loads and seismic loads, because the location of the interchange was exactly on a geological fault. Therefore, a seismic coefficient had to be implemented in the stability analysis as well. And the third loading case was the permanent situation with live loads and dead loads and accidental loads on the barriers. On top of the walls there were road structures, and the barriers were integrated part of the pavement design, and therefore an impact load of a truck or a car hitting the barrier, of course, can have an impact on the stability of the wall itself. So it needed to be implemented in the stability analysis. Here you can see two typical examples, one with Bishop sliding planes, the other one with a slice method, vertical or rectangular slice sliding planes. And by the implementation of the codes using partial safety factors and partial load factors on the driving forces, the stability analysis was performed. Now we go to the construction of these walls. We had a lot of experience with these type of wall structures in Nigeria, so we recommended to the Chinese contractor to work with sophisticated sliding formworks, which you can see on the left-hand side. Real life turned out to be a little bit different with the Chinese. They tried to use everything possible they could put their hands on, which resulted in this temporary formwork support during the construction. I have to say it worked, but it's far from ideal in my opinion. Here you can see the placement of the geogrid panels, which were cut at the right length, depending on the required anchorage length coming from the design. On the right-hand side here, you can see the geotextile, which is part of the wraparound detail to prevent that the filling material is going through the meshes of the geogrid and stays in place. You can also see that in the a minimal overlap was used between the geogrids, which are having this high strength in the direction to the wall. You can also see these temporary formworks here, which are supported like you saw here on the right picture. During the compaction of the filling layers, you can use heavier vibrating rollers, as long as you stay at least 1.5–2 meters away from the actual temporary formwork. And you can see that plate compactors are being used nearer to the wall. Important is always to move these compactors parallel to the facing of the wall. Otherwise, you have the danger of pushing the formworks outwards, and then you lose your alignment. Quality assurance. In this case, we are doing some compaction density tests. You need to achieve at least 98% proctor density after compaction in order to create a good and stable structure. Now here you can see how these formworks were placed. Here you can see that they have positioned the vertical beams with a slot inside. They are connected to the let's call it the base slab for the future barrier system, and that slab is integrated into the pavement structure. That means it has a stable, it sits stable on the top of the wall, and then they make a connection with these vertical beams with a slot inside, and then they can slide the elements from the top to the location where they need to be. And after each panel, a horizontal concrete beam has been placed, which you can see here, again with a slot, and this is how they build up their formwork. This is something that they designed themselves, the contractor, and it works very well. They also included some of their own symbols into this wall system, which you can see here, which gives it a bit of a better look. There were challenges during the construction of these works. First of all, when you're dealing with Chinese contractors, communication can be a serious challenge. Fortunately, in this case, there were 2 or 3 engineers who were fairly good. I will not say fluent, but they were fairly good in English, and that helped us communicate well. It also helped us in training the installation teams, which were typically supervised by Chinese engineers. Now, the installation teams again were local craftsmen from Ghana. So, but since the supervisors from the contractor, they were all Chinese, and they hardly spoke any English. So it was a bit of a difficulty, and sometimes we had to get the chief engineers on site to make sure that things were done in the proper manner. It was a first-time application of reinforced soil structures as well in Ghana. I have to say a first-time application of geosynthetic reinforced soil structures, because there had been another system applied before. I already mentioned that there was a geological fault on the zone where the interchange was being constructed, so that needed to be incorporated and included in the stability analysis. And the Chinese were very hot on using poorer quality fill, which was cheap and available locally. So we needed to redo the stability analysis based on the actual geotechnical parameters on site, and we had to push the Chinese very hard in order to do additional laboratory testing on these materials to make sure that we were working with the materials that were used in the stability analysis. Well, you have seen the formworks. That was a challenge, but in the end it worked well, but there was a lot of improvising and getting them vertical. The panel design was done by the Chinese themselves. Logistics is always an issue in Africa. You have to calculate supply chains of 2 months, 1 month on the water, 1 month to get it into the country at the right location. Then you're on the safe side. So 2 months is typical for supply of material, and that sometimes is a problem. Can be a problem, but it also is possible if you do proper construction planning. Communication I already mentioned. In the process of the project, there have been numerous design changes, and again, especially when you combine that with logistics, can be a challenge. But fortunately, we supplied materials in different time frames, so we could modify and change the sequence of construction based on the design changes, and we could manage it. Now, if you are more interested in this specific project, there has been a publication at the IGS conference in Rome on the same subject by myself, together with the engineering consultant, engineer Beng Pong. Interesting to know is that engineer Beng Pong got his master degree at the Delft University in Holland, and is now a very important engineer because he's also heading the Ghana Institute of Engineering. And also very interesting is that this project has won a series of awards by the FIDIC organization. The FIDIC is the International Organization of Consultancy Engineers. And 2 years ago, the Pokuase interchange as a whole project has won this award, not only because of the MSE structures, but due to overall innovative and sustainable thinking in the project design and implementation. And here on the left-hand side, you can see engineer Beng Pong. If you would like to see some small movies about the project in different stages of the project, you will receive these links, and then in your own time you can have a closer look. So now I would like to continue with a project on the other side of Africa. In this case, it's a project in Uganda, and now we are going to talk a little bit about base reinforcement in road pavements. In this case, it concerned a road in the western part of Uganda, and we have used geogrid reinforcement to strengthen the subgrade, and we have used geocells to strengthen the base layers in this project. The project team, the client was the Uganda National Road Authority. Contractor was SAICO, which is a Chinese contractor again, very typical in Africa. And the subcontractor and installer was Dynaco, which is a local contracting company in Uganda, working as a subcontractor to SAICO. The design and supervision was done by UNRWA themselves, the National Road Authority, and the proposals, the alternative proposals, and the designs for those were made by Admir Africa. The actual funding of this project was done by the National Road Authority as well. Location, here we can see Lake Albert, and here we can see Hoima. And Hoima is under serious development due to the fact that in the area large quantities of oil and gas have been detected. So the whole area is under development, and because of that, they needed to upgrade the existing infrastructure. One of them being the Hoima Butiaba Wonseko road. Now, again, this project has been managed by my colleague in Uganda, Brian Okello. I'm not sure if he's online, but if he is the guy to address most of the questions too, but I will do my best from my side to answer the questions as well. Project challenge. Here on the right-hand side, you can actually see that there was a bearing capacity issue in the location of the road structures. This is also due to the fact that these are floodplains from Lake Albert, so meaning that there were a lot of silty and clay deposits in the area, which created some premature failures already in the existing road structures. And further investigations have indicated that typical CBR values well below 3 were present on different locations. Silty soils, CBRs below 3%. Another challenge was that the quality stone base for the base layers was not available on short distance. So long haulage distances for fill material were a given fact. Therefore, both the client and contractor were very interested in options, solutions, where they could optimize or minimize the use of this high quality fill and maximize the use of fill which was readily available. Now, most of you listening, then you know the effect or the principle of base reinforcement to stabilize the base of road layers and to further improve the stress distribution and create a stiffer layer, thereby increasing the bearing capacity. These principles can work via interlock, via increased shear strength, etc. And the 2D effect is very well known with biaxial geogrids. But in this case, we use not only the biaxial geogrid, but we also use the more confining elements of geocells. And geocells, they are three-dimensional type of reinforcing structures where you contain the base fill material within the cells and create an even better plate bearing effect in the road-based structures. How does that work? A very simple experiment can be if you have a little bit of sand in your garden, you start standing on it, the sand will move in all directions. But if you put it in a bucket and you stand on it, immediately you have this confining effect, which in the end also increases or improves the stress distribution to the subgrade. I don't know what happened now. This goes too fast. Here you can see it in a more graphic manner. The principle of three-dimensional reinforcement with geocells is that you can actually create a much wider stress distribution via this 3D effect. And if you do that in a more scientific drawing, you can see here that if you do not have this distribution, you will have high stresses on your subgrades, you will have a smaller distribution, and you will create more displacement, more deformations and settlements due to this more concentrated load. Now, if you manage to do that in this manner, with a wider load distribution, an improved stress distribution, and you can create much lower displacement due to the fact that you have much lower stresses at your road base. That's basically the principle. In our first discussions, we worked with sketches like you see on the right-hand side, making alternative proposals with combinations of geosynthetics. But in general, what we did is we went to the site, or my colleague went to the site, collected as many data as possible, came up with first design or technical proposals. Eventually, different proposals were analyzed also on feasibility. In the end, the chosen ones were tried in trial runs, and at the end, the solution that was implemented was approved. The design process, well, the design of reinforced road bases, there have been many technical papers on the issue, and in the end, most of them are empirical, based on laboratory testing and specific material properties. So a lot of manufacturers of reinforcing materials have their own set of rules based on test data collected over the years. And that's exactly what has happened here as well. At the same time, they also link to existing standards like the BS 8006, the German standards, European standards, and ASTM standards when it comes down to soil geosynthetic interactions and material properties. At the same time, what my colleague tried to do is also align with the existing road design manual in Uganda and try to incorporate the geogrid and geosynthetic cell options within those codes, or at least to work in a line, to work in not in accordance, but together with the set of rules set in these design manuals. In the process, subgrade analysis was done, surface analysis, modulus, improvement factors, etc. I'm not going to go into details now. You can read it in the paper. I will also share a paper on this project via the NGO. So if you are interested, the paper can be sent to you. Also, the traffic loading was implemented in the design process, and let me see. Oh yeah, the design method is basically based for the GeoCell solution was based on research done by Han and Professor Leshinsky in the United States, and they have published a design manual for this type of system. And again, this design manual can be made available for those interested in these solutions. So I will, again, it's going very fast. Here you can see a comparison of the original design for the roads, and on the right-hand side, you can see the revised design. Now you can already see that there was a saving on the pioneer layer, the rock base layer, but there were also savings made in base layers, and this resulted in an overall saving of approximately 20 centimeters of pavement structure. And in a location where quality fill materials were not readily available, this was a serious cost saving. But beside that, it was also a significant sustainability advantage, because less kilometers of traffic or of construction traffic were allowed, and less use of base construction materials were required to build this road structure. The achievements of the design were, in the end, a reduced pavement thickness, use of locally available fill as a blend in base layers, thinner pavement structures, improved road performance, which in the end is going to lead to lower maintenance cycles, and reduced stresses on the subgrade, which was very soft. And I already mentioned the economic and the ecological advantages. Some pictures of the actual works. On the left-hand side, you can see the biaxial geogrid being unrolled and positioned on the prepared subgrade, the improved subgrade. Here you can see the actual placement of stone-based fill, the first fill layer, on top of the geogrids. Very important is not to drive directly with your truck on top of the geosynthetics, because the geosynthetics are not fit for immediately driving on top of it. Here you can see on the left-hand side, you can see the fuel cells as they are brought to the side. They are fixed to the pins, which you can see here already placed. And after that, again, same principle, don't drive directly on top of it, but use the method of first placing your fill and then drive on it. The actual fill operation I will show you again. And of course, quality assurance is very important. In this case, on the left-hand side, you can see that a small sand cone is being taken from the base layer over the geogrids, and actual density is being measured to make sure that they are installed in accordance with the specifications. And after the installation of the geocells and the base layers, a falling weight deflectometer testing was done to make sure that deformation criteria were met. Challenges during the construction were on the left-hand side, you can see a team of Dynaco waiting for material to arrive. Sometimes at the very last minute, the main contractor, the Chinese contractor, gave a signal to the subcontractor that no material was arriving, and that created situations like you see here. Everyone is waiting, and they were not able to work, which is a serious problem for a subcontractor. On the right-hand side, you can see what the road could look like after some in the rainy season, let me put it like that. And you can see that the subgrade driving sometimes was nearly impossible, especially for two-wheel vehicles like motorcycles and alike. So those were serious challenges during the construction works. There were others, but these are two typical examples. And at the end, all the news is good. So here you can see the actual project commissioning by the president himself. The road is being opened. And again, I would like to say special thanks to engineer Brian O'Kello, who has done these works and has guided these works in the most perfect manner possible. That is basically what I would like to share with you today. Any questions?
Thanks very much, Max, for your nice presentation. Interesting to see. The projects look very good, and I think yeah, some impressive solutions also. And I think it's a nice tie-in also to the presentation from Adam. So thank you. I think we have quite a few questions, but I think we have to kind of limit them in terms of time because we're already overrunning on time. But if people need to leave because they have something else, obviously they're always free to leave. The first one was from Serkan Sari. He's asking about the filling and the compaction order. When to do the filling first at the front and then at the back area, regarding the compaction energy transfer to the facing. I think that is what his question is. And there was another question from the same person asking, is it possible to fill back first and then close the facing area? So maybe you can elaborate a bit on how the site team installed the geogrid in terms of filling, compacting, and then placing the next layer.
Yeah. Well, this concerns the MSE structure. There are basically two types of MSE structures possible. One of them is what Adam showed us, where the facing element, in that case a sheet wall, is an integral part of the MSE structure, and therefore it is supporting the compaction. Now, the type of MSE structure which I have demonstrated, which I have presented, is what we call a passive system, where the formwork is a temporary one, and the actual compaction is taking place in different layers of 30 centimeters lift, approximately. So what you do is you have a stable base, which is well compacted, 98% proctor density. You put your geogrid on top of that base. You fold it over the temporary formwork. Then you put your fill layer and you create a well compacted first lift of fill. After that, you put a second layer of fill. In this case, we work with the spacing of geogrids of 60 centimeters, so two lifts of 30 centimeters. You put your second fill layer, you compact it again, and to reach the 98% proctor density. And during the actual compaction, you have to be careful not to push the temporary formwork outwards. Therefore, the compaction orientation should always be parallel to the temporary formwork. Now, once you have compacted that, you can start folding back your 1.5 meter flap of geogrid into the future reinforced soil. And then you can create sort of a mini channel in a V shape, what we do typically, to stick it there and fill it up with some extra fill to make sure that you create some sort of extra tension at the facing while compacting the layer on top. I'm not sure if I've answered your question properly this way. Did it make sense to you?
Yeah, it made sense to me. Yeah.
Thank
So
you.
in the end, yeah, I think you want to make sure then that the facing system you use, you compact against it, but you don't actually displace it. And I think in terms of in your view, Max, does it matter whether you fill at the facing side first or at the backs, all the way back from the facing?
You fill it up all the way over the whole area while compacting. Yeah, no, first you fill it up all the way, and then you compact it, and then you create the wraparound detail.
Yeah, I think that answers the question. Thank you. So the next question was, what are the key differences between PET and PP, geogrid retaining wall systems, in terms of material properties, performance, and applications?
Okay. Now, the most important differences between polyester and polypropylene are the creep behavior. Now, as long as if you use polypropylene geogrids, by the way, polypropylene geogrids are typically produced as biaxial geogrids for base reinforcement in road structures. But if you would use polypropylene geogrids for MSE structures, you would have to use a creep factor which allows, let's say, 60 or 120-year design lives and continuous loading. That means that you have a very high creep factor in order to define the allowable design strength for a PP product. In most cases, working with PP, that is not an effective result with a PP grid. With polyethylene or with polyester, it can be very positive. It can give positive design lives. So that's why typically MSE structures are using either polyester or polyethylene geogrids. In specific cases, they can also use PVA geogrids, but preferably is to work with lower creep polymers because of the longer design lives of these type of structures and the creep sensitivity.
Thank you. I think there are a number of more questions. It might be suitable to answer the questions outside of the presentation, because I think we're overrunning out of time so much that that makes sense, unless you have a lot of time left, Max, to answer, because I think there are another 5 questions or so.
I'm available.
Okay. Well, let's do it now. There are a number of questions regarding the geocells. One is what your view is on the cyclic load acting on the geocell, and if there is any special creep property required. The other one is whether there's a minimum thickness fill that allows traffic over the geocell during the construction process.
Okay. Well, first of all, the material properties, I believe that there is an effect, a long-term effect of the actual creep properties of geocells. A lot of geocells on the market are manufactured either from polypropylene or polyethylene. I believe that on the longer term, these may be a little bit more susceptible to permanent deformations and translated into rutting of the structure on the long term, than, for instance, the material that is used in the product that we use, which is a neolloy blend, which is a low creep sensitive product. So I believe it has an impact. Yes, absolutely. Now, the second question was, do you need a minimum fill on top of your geosynthetic prior to driving on it? Yes, we recommend you have at least 5 centimeters of fill over the top of the geosynthetic. Yes.
Yeah. Okay. Yeah. There's 2 questions on the geogrids. The first one is, does the overlap length between the geogrid affect its performance in terms of a reinforcement application? The other one is, you showed, I think, a cross-section with the geogrid setups for the MSE walls. And on the cross-section, you could see a section of the geogrids are longer at the bottom and shorter at the top. And Serkan is asking, the top lengths are usually longer. Why is it shorter in this case?
Okay. Well, first, the overlaps in the high strength direction of the geogrids in an MSE structure, we do not work with overlaps. The overlaps are only in the cross direction, and that is not the main strength or force direction. Therefore, the overlaps are strictly, let's call it, functional or structural. Yeah. So you need to be sure that on all area you have horizontal reinforcement perpendicular to the wall facing, because that's where you need your strength. So a minimal overlap is required to make sure that in all times you have sufficient coverage, but it is not essential for structural reasons, apart from walls which work in an angle. Yeah, then you may need to have an overlap in the cross direction. Yeah, because you need to reinforce those walls as well. The second question was, again, Robin?
Yeah, the second question was, if you look at the cross-section of the MSE walls, there's a difference in length between the bottom sections and the top sections. So the question is, why is the bottom section longer than the top section in your cross-section?
Mostly this has to do with the global or external stability. If you are constructing walls on soft soil, you want to push your bishop sliding plates outwards as far as possible to create very large circles. Large circles, sliding circles, means more shear resistance. And via extending the geogrids at the base of the wall, you are pushing these circles further away and making them larger. Yeah? So that's basically the principle of using longer reinforcement at the base. For economic reasons, you can optimize going upwards if you do your stability analysis. So that follows from the stability analysis done with the software you are using.
Yeah.
Does that answer your question?
Yeah, I think it does. And I think the question maybe arose from the presentation by Adam, which shows the inverse, essentially. So they show a longer section at the top and a shorter one at the bottom, which has to do with the active zone that's behind the sheet pile wall that is being modeled. So the active zone goes from the bottom to the top, but it moves outwards, so you need a longer length at the top and a shorter one at the bottom to stay outside of the active zone. I think that's the concept for the, unless I'm mistaken, Max.
But sometimes in practice, when you are constructing or when you're designing a wall in a mountainous area, you simply do not have the possibility to extend very long at the base. Sometimes you can even make a connecting system of reinforcement to, let's say, a rocky environment. This has been done in the past in structures, but it's more complicated. It needs much more detailed engineering and design in order to implement that. Also, sometimes it's not possible because you do not want to disturb an existing geological profile, but at the same time, these can be the sensitive parts of the structure. For instance, if you create pressure water at the toe of an MSE structure in a mountainous area, those can be the destabilizing locations for the overall stability of the wall. So you have to pay attention there.
Yep. Okay, thank you. I think on sort of the same topic, if you have to overlap on the MD direction, what would be your recommendation? Because roll lengths are usually not exactly fit to the project lengths. So I suppose the question is asking if you overlap in the uniaxial strength direction, perpendicular to the wall, what would be your recommendation?
Rule number 1, don't do it. Rule number 2, if you simply cannot evade doing it, do a proper shear transfer calculation based on the interface shear strength between geogrid and the surrounding soil, and the length required to design this overlap. But rule number 1, I prefer don't do it.
Clear. Okay. Another question, has RAP, I'm not 100% sure what they mean by the abbreviation. I don't know if you know, Max.
RAP.
Yeah.
It has to be explained to me. I don't know.
Reclaimed asphalt pavement. Has reclaimed asphalt pavement been used with geocells in construction projects? And if so, could you provide any case studies or examples that demonstrate the performance and the benefits of using it with geocells?
I'm not sure if that has been done, but I can ask the question and respond to that at a later stage.
And we can include that in the sharing of the presentations as we put it on our website.
Okay.
Okay. Let me see. I think that answers all the questions, unless people have more questions. I went through all of them. What we will do is we will PDF all of the presentations that we've seen today, and we will place them on the website of the NGO. So that is for reading material for anyone that likes to read them afterwards. We also have a recording of this presentation that we might share at a later stage. So thank you very much, Max, for your interesting presentation. I think it was great to see. And
thank you for listening.
Yeah, no problem. And thanks all the attendees for attentively listening to the presentation and asking so many questions. And we hope, as the Dutch chapter of the IGS, that it was an informative technical lecture, that people got some information and maybe some new insights on how to use geosynthetics in projects. And we hope to kindly see you at our next event. And we have the general meeting for the Dutch IGS in November, which is the in Dutch Algemene Ledenvergadering. So if anybody is available to join that, feel very welcome. And that will be posted on our website also. So thank you, everybody, and have a good day.